This is an atom. Let's get rid of its electrons for the moment and let's just focus on the nucleus. The nucleus of an atom may encounter two types of processes. The first one is the spontaneous disintegration process, where the nucleus spontaneously disintegrates. The second one is the so-called nuclear reaction, where the nucleus interacts with another particle or another nucleus. These processes are called nuclear processes, and both of them are characterized by an emission of some kind. This emission may be corpuscular or electromagnetic, and they represent the so-called radiation. We will focus on spontaneous disintegration processes that determines the so-called radioactivity of an element. So when we say, for example, that uranium is radioactive, we actually mean that the nuclei of the atoms of that substance are spontaneously disintegrating themselves and releasing some kind of emission, which is the harmful radiation we all have heard of. What do we actually mean with spontaneous disintegration processes? Well, the technical term is decaying. The components of the nucleus are decaying, and let's see some examples. Alpha particle is a corpuscular emission, so a corpuscular radiation that comes from alpha decay processes. Alpha decay processes happens in a heavy, unstable nucleus, for example, uranium. Here, the nucleus spontaneously releases 2 protons and 2 neutrons binded together in order to get lighter and more stable. This is nothing but a nucleus of helium, which represents the alpha particle. We can represent this process as it follows. So for a given element of Z protons and A nucleons, where A is the number of protons and neutrons together, we get to an element, a lighter element of Z minus 2 protons and A minus 4 nucleons, because we are losing 2 protons and 4 nucleons, 2 protons, 2 neutrons, plus the alpha particle. Beta particles. Beta particles are another example of corpuscular radiation that come from beta decay processes. We may have beta minus decay and beta plus decay. So let's see beta minus decay first. Beta minus decay happens in nucleus with a high number of neutrons. So we have more neutrons than protons. And the neutron spontaneously decay into a proton, an electron, and an antineutrino. The proton stays inside the nucleus. Meanwhile, the electron and the antineutrino are emitted. So we can represent this process as it follows. So a neutron decays into a proton, an electron, and an antineutrino. And the electron represents our beta minus particle. Beta plus decay is similar, and we have a high number of protons, so we have more protons inside the nucleus than neutrons. And spontaneously a proton decays into a neutron, a positron, and a neutrino. The neutron stays inside the nucleus, and the positron and neutrino are emitted. Similarly to before, positron represents our beta plus radiation. Gamma rays. Gamma rays are an example of electromagnetic radiation. Nuclei, similarly to the shell structure, to the electronic shell structure of the atoms, have discrete energy levels. Well, transitions between these levels causes the emission of an high energy photon. The frequency of this photon is proportional to the difference of energy between the levels. This is quite common because we may have, following a decay, an excited nucleus. And by exciting that nucleus, we may have an emission of an electromagnetic emission, high energy photons. All the elements of the periodic table are classified by the number of protons, Z. Z is the number of protons. For each element of number of protons, Z, we may have variation in the number of neutrons. These variations represent the isotopes of that element. We may have some isotopes that are stable and some isotopes that are unstable, because the ratio between protons and neutrons may be balanced or unbalanced. Let's now see some examples. Alpha decay. Let's take polonium-210. Polonium-210 is the 84th element of the periodic table. You can find it bottom right. This isotope decays as an alpha decay, so it loses 2 protons, so we get to lead, 82nd element of the periodic table, and 4 nucleons, because 2 protons and 2 neutrons, so we get to lead 206, 82 protons, plus alpha particle, the release of the alpha particle. Beta plus decay. So, in beta plus decay, a proton decays into a neutron, a positron, and a neutrino. Let's take, for example, magnesium. Magnesium-23. Magnesium is the 12th element of the periodic table, so we have 12 protons. In beta plus decay, a proton spontaneously decays into a neutron, a positron, and a neutrino. So we're like transforming a proton into a neutron, so we are losing a proton. We get to sodium, 11 protons, but we have the same number of nucleons, so always 23. So sodium 23 plus positron and neutrino. Beta minus decay. In beta minus decay, a neutron spontaneously decays into a proton, electron, and antineutrino. Let's take carbon-14. Carbon is the 6th element of the periodic table, so we have 6 protons. A neutron becomes a proton, so we are like gaining a proton. So we get to nitrogen, 7 protons, but we have the same number of nucleons, so always 14. So we get to nitrogen 14 plus electron plus antineutrino. Now, let's get interactive. Click the link in the description and follow me through this interactive table so that you can understand the principle I've just explained. So, click the link in the description and come back to the video and follow me. So, click on decay mode here in this table and let's study this thing. So, this is the so-called table of nuclides. This table represents all these isotopes for each element of the periodic table. Let me explain. As you can see on the x-axis, we have the number of neutrons. Meanwhile, on the y-axis, we have the number of protons, Z. So, for each element of the periodic table of number of protons, Z, we have all the variation in neutrons of that element. So let me just zoom here and makes things clearer. So let's see carbon, or carbon, where is carbon? Carbon, you are all familiar with carbon, is the 6th element of the periodic table, so we have 6 protons in the carbon atom, right? Here are all the variations in neutrons of the carbon. So we may have, for example, carbon-12, which have 6 protons and 6 neutrons. This is the most famous isotope of the carbon. This is always carbon, right? Carbon-12, 6 protons, 6 neutrons, and is a stable element, as you can read here on the top left. All right. We may have carbon-11, for example. Carbon-11 is not stable. It's always carbon because it has always 6 protons, but we have 5 neutrons. The ratio is unbalanced, so it's not stable. It decays as a beta plus decay. All right. We have all the variation in number of neutrons of carbon here on this on this line. or as you can see, this is repeated for every element of the periodic table. So repeat this process for every element of the periodic table, you get this table, alright, table of nuclides. As you can see, we have different colors, alright? We have this black line here. This black line represents all the stable elements. The pink represents the beta minus decay, the blue color represents the beta plus decay, and the yellow represents the alpha decay. Let's see the example I've made earlier. Let's see magnesium 23. As you can see, magnesium is a 12th element of the periodic table, 23 nucleons, and decays as a beta plus decay. So what happens in beta plus decay? A proton becomes a neutron, basically, alright? So we are losing a proton, alright? We are losing a proton, but the number of nucleons is the same. So we started from magnesium 23, and we have to lead to something that have the same number of nucleons. So minus 1 proton, but same number of nucleons. So we get to sodium 23. Let's see this again. Down by 1, right by 1. Right? Down by 1 because we are losing a proton. Right by 1 because we have the same number of nucleons than the starting point, right? The starting element. So magnesium had 23, so we get here. Now, let's see carbon. Carbon 14. Carbon 14 decays as a beta minus decay. So a neutron becomes a proton. Okay, spontaneously, a neutron decays into a proton, but basically a neutron becomes a proton, alright? So carbon is like gaining a proton. So we are moving up by 1. On the x-axis is the number of protons. So we are moving up by 1 because we are gaining a proton, but the number of nucleons is the same. So we started from 14, carbon 14, we get to nitrogen 14, alright? Because it's like we are gaining a proton by losing a neutron, right? So up by 1, left by 1. Or of course, this in beta minus decay. In beta plus decay is the contrary, right? Down by 1, right by 1, right? So beta minus decay is this. And as you can see, beta minus is represented as pink, and the final element is represented as black because it's stable, right? It does not decay. Let's see the alpha decay I made earlier. It was polonium 210. Polonium 210 is right here. So here, all right. Polonium 210. Alpha decay. So what happens in alpha decay? We are ejecting basically a nucleus of helium. So 2 protons and 2 neutrons binded together. So we are losing 2 protons, right? So we are losing 2 protons, we're moving down by 2. So from 210, we move down by 2, and we get to lead, alright, 1 and 2. But we are also using 2 neutrons, so left by 2, and we get to lead 206, from polonium 208 to lead 206. As you can see, lead is the last element of the periodic table that have stable isotopes. This is the heaviest element, the heaviest stable element of the periodic table. So you may ask, what happens to, for example, uranium 238, right, which is pretty far away from lead. As you can see, how can this process of alpha decay get to a stable element? Well, it doesn't. Simply it doesn't. We are, as you can see, we are pretty far away from a stable element. And uranium 238 decays as an alpha decay. So we lose 2 protons and 2 neutrons, and we get to thorium 234. But this is unstable and decays as a beta minus decay. So what happens? Well, we get up by 1 because we are gaining a proton from beta minus, remember. a neutron becomes a proton, basically. So we're gaining a proton and losing a neutron, basically, no? So up by 1, left by 1, beta minus decay again. So up by 1 and left by 1. We get to uranium-234, again uranium. Well, this is a different isotope from the starting element, right? We started from uranium-238, we get to uranium-234, right? Which is a different isotope. So alpha decay, again, down by 2, left by 2. Alpha decay, again, down by 2 and left by 2. As you can see, we are moving in the direction of lead. We are following this process. And if you are patient enough to make all these movements right, believe me or not, you get to lead, alright? So down by 2, left by 2, again, down by 2, left by 2. Believe me or not, somehow you get to lead, following this chain of processes, of decays, chain of decays. Well, this is a well-known chain, well-known series, right? Which is called uranium series or radium series. I think it's the same. And this is simply a process, a chain of processes, all right? From uranium-238, alpha decay, thorium, beta minus decay, uranium, alpha decay, thorium, alpha decay, radon, alpha decay, Rn, I don't remember, alpha decay, polonium, until we get to polonium-210, alpha decay, lead. Alright. It's radium. Right. I missed that. As you can see, the last piece of this chain, alright, so from polonium-210 to lead-206, is the example I've made earlier, right? So it's the last step of this chain. So heavy elements may follow a lot of processes before became stable, right? So that's it. That's it. For today, I would like to stop. We have seen a lot. Thanks for having watched so far. Subscribe to the channel and hit the like button if you enjoyed the video. Also, follow me on Instagram at Atlas Humanity. You can find a bunch of stuff you may enjoy. Also, don't forget about the PDF you can find in the description as an offline reference to this video, this lesson. You may need to read something about this lesson in particular. So you can find it on the description. See you to the next video. Thanks.